Good morning, ma'am. And my AIT TikTok video is a deep dive into cache memory design and performance of the cache memory. So, the CPU memory gap. Okay, the CPU memory gap. CPU have evolved at a exponential rate, far outstripping the speed improvements in of a main memory. This creates a significant bottleneck that cache as a bridge. Cache memory serves all a small, ultra fast buffer, strategically positioned between the CPU and the slower main memory. Performance multiplier. Its role is critical in this session. So, dramatically reducing CPU idle time and accelerating instructions executions are leading to superior overall all special performances. So, the origins and evolutions of this cache memory. The concept of cache memory emerged in 1968 with the IBM system by 360 model of 85 featuring a 32 KB cache memory with a 240 nanoseconds access time. So this is the first cache memory that is evolved from our history that early implementations were designed to bridge the speed disparately between core memory and slow drum storage. Today, Cache has evolved into complex multi-level hierarchies like L1, L2, L3, directly integrated into CPU dies and becomes an indisputable component from modern high performance computing. So core design of this in a cache memory. So cache size and block size, mapping function, replacement algorithm, or writing policies. These are the main subtopics. And the cache size. Optimizing for speed, small, fast caches are crucial for significant performance uplifts. How the cache is more important. This line says here, and the block size. Finding the balance between exploiting locality benefits and mitigating this catchy populations. Mapping function. Uh, Diverse techniques including direct, fully associative and set associative or data placement, replacement algorithm, strategies like FIFO, LRU, FIFO in the sense first in, first out, and LRU and random replacement to manage this catchy eviction effectively and efficiently. So, right policies choosing between right throw and right back mechanisms. Each performance is a trade-off performance in this core designing catchy memory and memory locality. The principle behind effectiveness and the memory locality holds the catchy effectiveness because the memory is more effective in this catchy memory word that temporal locality data accessed recently is likely to be reused in near future. Catchy leverages this be keeping frequently used items in close. So this catchy memory in a simple words we can say that it is a recent in our Windows or else it's the recent in our mobile phones and a spatial locality. If a data item is accessed, its neighboring data items are also likely to be accessed soon. Cache blocks exploit this from efficient prefetching, efficient data transfer. So in this cache memory, the data is more efficient and it is up to it is more easily transferable. So cache lines or blocks are designed to exploit both temporal and spatial locality, enabling the system to prefetch and store relevant data, minimizing the transfer access. So this is about the memory locality of this cache memory effectiveness, and the cache has it a separate hit ratio that is denoted by H. The probability that is requested data is found in the cache. The higher hit ratio means the better performance. If the H value, the hit ratio value is more, then the cache memory performance will be the better. And the miss ratio, calculated as one hit ratio, represents the percentage of times data is not found in cache, incurring the performance plan. If the data is not found in this cache memory, it is called as a miss ratio. And average access time. This a crucial matrix as calculated as cache access time plus miss ratio into miss penalty. This crucial matrix, the cache access time. When the cache is accessed, it contains some particular time, and the cache plus this miss ratio. If the data is not found, then the ratio into miss penalty. There will be a penalty of this miss penalty. It gives the total time of this crucial matrix. This denotes the real world speed benefits. This average access time is the real world benefits. This demonstrates okay. For perspective, an LI cache hit might take 1 to 2 CPU cycles, while the main memory can take 100 cycles. Secondary main memory can take 100 cycles. So this cache memory, when it compares to secondary memory, the cache memory is more effective, more efficient when compared to secondary memory. Next to it, types of cache memories and their impacts in the real world. So compulsory mesh, uh, an unavoidable miss when data is accessed for the very first time and must be loaded into the cache. Capacity miss occurs when the working set of program is larger than the cache's capacity, leading to data being evicted and re-requested. So conflict miss. This conflict miss can happen when multiple memory blocks of a map to the same cache line, causing frequent evictions despite available cache space. So coherence miss. This coherence miss is nothing but specific to multiprocessor systems. This miss occurs when the cache is invalidated by the write operation from the another processor. When the cache is unavailable, this coherence miss may occur in this impacts. So advanced cache design technique use. So vitamin cache, sorry, victim cache, a small fully associative cache to store recently evicted blocks, reducing conflict misses. The sub blocking, dividing cache blocks into smaller sub blocks to reduce their mess penalty by only fetching required data. So memory banking, organizing memory into independent blocks to allow parallel access and reduce latency. Split versus unified cache. Separate instructions and data caches. Data caches are also called as a splitter. So data caches are a single cache of both unified. This unified is a single cache of for the both. So split caches improves bandwidth by allowing simultaneously fetching this one. So this is the difference between split and unified cache. Non-blocking caches allow the CPU to continue processing other instructions while a cache is in being handled, improving the cache power. And the real world impact and the sorry and the diminished caches, multi-level diminished performance that gains. So multi-level caches, modern CPUs like the Intel Core i9 employ sophisticated multi-level cache hierarchies L1, L2, whereas L1, L2, L3 and bridge the gap between CPU speed and main memory latency. It's a very high speed processing. So L1 cache, the typically around 32 kb, offering ultra low latency of approximately 4 cycles. This crucial for immediate instructions and data access. So L3 cache, often the larger shared cache is more than 30 MB, that serves all cores, further reducing access time. And here I didn't mention the L2 cache, maybe sorry for that. And the L2 cache is that can provide from 32 kb, nearly it provides 32 kb to, I think it's for up to 2 MB change. So that is L2 cache. The cost of no cache. Without this finally the turn cache system, CPU stalls dramatically increase, bringing applications of performance. Otherwise, the truly enables the speed we experience here. And here comes the conclusion of a cache memory that using hero of computing. So here the word hero of computing defines the um, importance of a cache memory, that balanced design, continuous innovation, optimization key, and the future in this cache memory. This cache designs a meticulous balance of speed, capacity, complexity, and cost vital optimal performance and continuous innovations. Ongoing advancements in cache technology ensure that it keeps pace with the relentless progress of CPU architectures and optimization key. A deep understanding of cache memory is indispensable of both software and hardware engineers seeking to maximize this system performance. And this is the future of cache memory. Expect a smarter, more adaptive cache designs and there are deeper integrations with emerging technologies like AI workloads. This AI workloads has the most power in this cache memory. If this cache memory has got this AI workloads, then this will be the most effective for every software user, not just the software user. In different ways, it's it's gonna be different. So this is my topic. Thank you.